Good morning, everybody, and welcome to this week's JKMRC Friday seminar. My name is Nathan Fox from the W.H. Bryan Mining and Geology Research Centre at the University of Queensland. At the JKMRC today is Professor Rick Valenta. He's the Director of the BRC and the Acting Director of the JKMRC. And Rick will be moderating the questions from the audience today at the centre. But thank you, everybody online, for joining us as well. Before we begin, on behalf of the SMI and the University of Queensland, based here in Brisbane, we'd first like to acknowledge the traditional owners of the land on which we meet today, and we pay our respects to their ancestors and their descendants. Today it's a pleasure to introduce David La Rosa. David is the Principal for OreControl Blasting Consultants. David graduated from the University of Queensland in 1987, and he spent 15 years at the JKMRC conducting mining-related research under a range of AMRO projects. During this time, David was responsible for instrumentation and software development at the Mining Research Group as a Senior Research Officer. Before David then joined Metso Process Technology and Innovation, where he was a General Manager for Products and the Manager of Mining Technology. In 2016, David joined CRC Ore as a Principal Mining Engineer, where he's been focused on grade engineering applications. But David's really been involved in the invention of multiple ore tracking technologies, including smart tags and BBMs, which David informs me of blast movement monitors. And he uses extensive industry knowledge to practically solve complex solutions, complex problems. So in 2018, David co-created OreControl Blasting Consultants to create systems to improve value for surface mines through optimizing post-blast ore control. So highly relevant in today's world. Today's seminar, David's going to explore grade control in 2020, particularly under the current conditions where we're all kind of limited by the coronavirus. But David uses a strapline here, which is there is always potential to innovate and improve a gadget or process, no matter how mature the technology may seem. And I think that's very wise words going forward. So I'd like to pass over to David now. For those online, please ask questions in the Q&A section of the Zoom link. So thanks, David, over to you.
Thanks, Nathan. Thank you, everyone, for coming. I hope everyone's safe and well here and out there. Thanks. So I kind of struggled for a catchy name, and this is my catchy name, and hopefully I'll be able to join the dots between grade control and coronavirus. So as Nathan said, I started here at JK 32 years ago, so this tells us something about our age. And right, yep. So yeah, JK days. There's a whole seminar in that. You know, in 15 years, did a lot of interesting stuff. I'm a digital hoarder, and I have a huge archive of really embarrassing photographs from my past. So I've got a bit of a preamble ramble here. This is myself and Andrew Tunstall, who used to be the JK's manager in Chile, and this is us in a quarry in Colombia. I think it's 94, 95. Note the lack of PPE. Even if I did have a hard hat, I don't think I would have got it over that 90s hair. There's also a donkey there, which was, I think, Alan Cocker et al. Used to take some blast monitoring equipment up to the top of the hill behind Chuquicamata. Of all the things I did here, there's lots of interesting things. This has got nothing to do with grade control, by the way. This is just, it's pandered to me. Some of the interesting things we did here, yeah, with 1999, we had a diamond damage project with De Beers, where basically we took 24, I think they're 1 carat, half a carat diamonds, gem grade diamonds, and we stuck them in concrete, stuck the concrete in there. There's Gideon doing some work. We put the concrete in drums with a little explosive charge, and we were supposed to get nice shock waves to see whether or not the diamonds would be damaged by the explosives. Sometimes the drums didn't behave, and so we had to dig through and find them. And luckily, we didn't lose any of the diamonds. We were told in no uncertain terms not to lose any, so that was quite a bit nerve-wracking. And that's basically what we ended up with. So we had diamonds like so that sometimes survived, other times we never cracked them, but we got a number that just shattered internally. So the start of the grade control journey for me was in the 90s, the late 90s. There was a growing awareness in the industry that something wasn't right, that the what people knew was in the ground wasn't manifesting itself at the end of the concentrator. So there was lots of work done globally. using pipes and coloured sandbags and chains and some basic modelling. At the end, it came back to blast vector indicators, BVIs, which are polypipes, which have issues in recovery and also accuracy. You end up with a 3-metre pole where on that point is the end point of your vector. At the same time, we had a project in the mining group, blasting to customer specifications, BTCS, and that was mainly focused on machine productivity and fragmentation and wall control. But there was interest in trying to tackle this dilution and ore loss issue that was plaguing the industry. So the light bulb moment was in April 2001. Darren Thornton, who was working here at the time, showed me this paper where the Mackey School of Mines in Reno were doing some work where they had magnets in the ground. Pre-blast, they would go with a cesium vapor gradiometer, it's a magnetic detector, and pick up the vertical component of the magnetic field. So you end up with these little volcanoes of magnetic field. So that shows you where the magnets were pre-blast. And if you remember your high school magnetic theory, there's a dipole, and so that's all good. But then post-blast, you get something that looks like that. So what's happened? Obviously, with the blast, the magnets are rolled, and the magnetic field isn't always pointing vertically. So that night, I went home and I pondered it, and the next day I came back. I remember it fairly clearly. It's quite surprising. I said, what if we gimbaled that magnetic field so that the magnetic field was always vertical? So the JK Skunkworks kicked in down there, and that was Michael Wortley, Graham Sheridan, myself, Peter Holtham, and also Darren Thornton. And we kicked in, we built a prototype. It's a fun fact, when it came to choosing the frequency of this electromagnet, it was an AC system. We had been listening to Triple J downstairs, and there was a band called Salmon Hater, which had this song called 6.66, which is the 100th of the number of the beast. So, of course, we chose 66.66, which is 100 times the number of beasts as our frequency. So just remember that if you ever see a BMM in the field, the orange ones. So 23 months later, we came up with this prototype. This is at Sunrise Dam, and there's me with a big grin on my face when the two survived. Nick, who's here, he machined the first housings. There's a little polystyrene ball there that I bought from Spotlight, and we sort of MacGyvered it all together. But they worked, and we found them post-blast and created these vectors. And the rest is history for BMT. So 250,000 of the balls have been used around the globe, and they're pretty well known throughout the mining industry in grade control space. So as Nathan said, I'd forgotten I'd given you all that. I then subsequently left, went to Metso Process Technology for 7 years, did lots of mine-to-mill stuff, developed smart tags, which are RFID tags, again, tracking ore post-blast through the concentrator. Did some vision systems and acoustic systems. Then went back to BMT, which had, was growing then. So I spent 3 years at BMT doing R&D. I wrote the early version of the analysis software. Some would say in an ad hoc fashion, but it was fit for purpose. And actually in 2012, we won the I Awards, both in Queensland and nationally, for the industrial design of software. So that was pretty cool. And we also tripled the BMM sales in that period. I then went back to Metso, as you do, and did some more stuff. That imploded in 2015, and so then I ended up at CRC, where that's my day job, doing blast modelling in the great engineering space for induced and natural deportment. Also looking at mine-to-mill studies and using the capabilities of the integrated extraction simulator with the blast fragmentation model, and also doing some data analytics to look at correlations between the sensors that we're analysing, excuse me, that we're evaluating, and the origins of the ore, again, looking at ore tracking. In 2017, sorry, I'll step back a bit. So in 2010, I interviewed Will Hunt, who's my co-owner of OBC, and he started at BMT, and then I left. And Will left BMT in 2017 with this with this understanding that there's a 3D issue in grade control and with a burning desire to sort of solve it. He had got some funding from Kinross, and he reached out to me, and I checked it with CRC, and we started OBC. So yeah, Will's a mining engineer. He's based in Denver. He's done a lot of consulting around the globe. Our CTO is Jeff, very clever software engineer. Had nothing to do with mining, which is probably a good thing. And yeah, has done a fantastic job with what I'm about to show you. So let's go back to grade control. So grade control 101. So you have a blast block. You do lots of assays and blast hole sampling. You do some magic geostatistics, and you create a grade control model. And that's used to classify ore and waste, and uses the grade, the geochemistry, lithology, etc. This costs a lot of money. It's very costly and time consuming. And then we do this. We blast it, obviously, to excavate and process it. So if we look at this blast here, so these are pre-splits, so it creates a crack along the high wall there, just for to protect it from damage. It doesn't really contribute to movement at all. This blast is going to initiate here and fire in a V shape. Drones have made our life much more interesting, and allows us to see things that we couldn't see before. So there you can see some fly rock coming to try to take us out. It doesn't, but so if we go back, we can see the rock at the front kicking out, like so. So we go down to the ground now and look at this blast, and we look at this for scale. This is a 10-meter blast. You can see these two guys here, the scale. So, you know, it's a lot of movement. A big power trough, or we call it power trough at the back of the blast, big heave here. So ore has gone from here to there and kicked out there. And so when you're looking at mitigating for blast movement, obviously things aren't sliding in a nice 2D manner. Stuff is going down and up and everywhere and forward. So we created OrePro. It's a big jump. There was probably 18 months of software development there. And it does two things very well. It creates dig line boundaries to your specifications. So grade and minimum mining unit, which depends on the size of the equipment, mining direction, face angle, and of course the 3D movement. So we end up with every time, it takes billions of calculations, we end up with the optimized polygons to capture the metal that you want. So this is an example of comparing our polygons with hand-drawn ones. We gave this as an exercise, we gave this to 4 geos. And you can see here, if we look at the dollar net, which is the metal minus the processing cost, you can see the great variation between the four geologists, and in terms of dollars difference between our polygons, and the worst case is $96, and our polygon and the best one it's whatever, $70,000. So sometimes it makes sense to take dilution, which is rock which has got no metal in it. Other times you have to wear a bit of ore loss to get your maximum recovery. Regardless of that complexity, the system always gets the highest value every time. So once we've got our perfect polygons, what do we do with them to take blast movement into account? So the old way of mitigating for blast movement was to basically slide them horizontally. And I'll show you what that looks like in a moment. So we take those 2D polygons and then we flag them in the field, and we push them to the digging equipment. But heave, which is how the blast swells, 3D movement and the shape of that post-blast muck pile is largely ignored. So even if everything was perfectly optimized pre-blast, everything has changed post-blast. So we look at this we look at a case study. So when this guy was standing, there were 2 blast movement monitors, BMMs, below him, and the top one, which is probably about 2 meters below his feet, moved all the way to there, and the bottom one moved to here. So sometimes the top one moves more, sometimes the top one moves moves less. It depends on the face conditions. So in cross-section, let's look at a representation of an in-situ vein, which is an accurate representation of that real-life scenario. We end up with something like that. So we've got a vector here and a vector there. So what is that? And just as a definition, a flitch is if you mine something in 2 passes, each of those passes is called a flitch. So if you do it in one pass, it's 1 flitch. If you do it in 4, there's 4 flitches. So in this case, we were going to mine it in 2 flitches, 2 passes. So the ore body post-blast looks like so. It's got this. It's been smeared across towards the free face, which was choked in this case. And we also know that from surrounding data that the floor of this blast has hardly moved. So what previously you would do, you would move the pre-blast polygons and move it across and project them to the surface. And then the shovel, if it digs from this direction, from the right-hand side of the screen, we end up with this material here being lost because the shovel is going to dig up to this line here, taking the mining angle into account. This is going to be sent to the waste dump. It will then keep digging until it gets to here. This yellow material will then be dilution. So that's material which has got no economic value, which will get sent to the processing plant. And then this material here will be lost again because it's sent to the waste dump. So what if we dig from the other direction? So we get a similar sort of scenario. So we widen the dig lines so that we eat lots of dilution. We get all the metal, but we also take a lot of non-economic, uneconomic material. Or do we narrow it so that we minimize our dilution, but still lose this material here? What if we dig in a single pass? What if this isn't a multi-flitch? You've got big equipment and you have to dig it in one pass. You end up with, going back to that, where do you draw the line? No pun intended. If you widen it, you end up with all this this dilution here. What if you go the different direction? So there's a lot of scenarios to consider. So the bottom line is that a human sitting in an office, a human, full stop, can't do these calculations in their head. There's billions of calculations and conditions which need to be taken into consideration, and neither can a 2D optimizer. So the solution must take 3D blast-induced movement into account, and dig direction, face angle, and the height of the flitch into account. So why does mining direction and face angle matter? So this is an extreme case. So obviously, if you're going to dig in this left-hand case scenario, you're going to move through here and get lots of dilution. In the second case, because everything lines up, it means you can clean that face of that vein and get a much more targeted, you can be much more targeted with how you recover that vein. So the solution that we've developed has got 3 inputs. So obviously there's the in-situ grade control model. We take the blast design, and usually blast hole, we want the timing, so we want to see the timing contours, and that gives us a good indication of how the rock moves. Measured vectors, if they exist, and if they don't, we've worked on a system we call smart vectors, which predict the movement based on blast design and the final post-blast surface. So we need the post-blast surface, which constrains the material to a known outcome. With those 3 inputs, which are fairly easy to get, I mean, the post-blast surface, people used to complain about it, but with the advent of drones, within an hour, you can get a really high resolution 3-dimensional scan of your post-blast surface. So what we create is a reactive model. What we call it, it's not a predictive model, it's a reactive model. So we take the blast design and the post-blast surface, and we say, okay, we knew where everything started, and we now know the shape of how everything ended. So we can join the dots in between the two and create this model. So it's not a physics-based model. We've tried a couple of them, Connie. And whilst they give you a good general idea of what the muck piles are going to look like, so far, for day-to-day grade control, we haven't seen them to be accurate enough or useful enough. I'm sure with the right people that we'll get there. So she's laughing. So with that reactive model, we create this vector field, and that vector field we then apply in the pre-blast grade control model and move everything from its pre-blast position to the final blast position. And we can then use our polygon, polyline generator to create the optimized grade control polygons, which take into account dig direction, dig face angle, those flitch elevations. And also, yeah, the cutoff grade. Yeah, what's the limit between what's economic and what's uneconomic? And it doesn't have to be as simple as a cutoff grade of 0.8 grams per ton. We can also do really complicated decision trees. So where you can do sub-classifications. So this is, Jeff's coded this up. It's quite as I said, he was quite clever, and this is quite a special thing. So we can use these decision trees to say where material is going to go. It's all about decisions. It's not just a decision to send something to the waste dump or send something to the concentrator. There's multiple stockpiles, and is something acid generating? Should it go to the leach pad, etc. Just some screen grabs, gives you 3D situational awareness, so you can look and see how things all fit together. And we do financial analyses to compare what we have generated with what the mine might have generated, either hand-drawn polygons or generated by another package. So we look at a case study. This is real. So we look at, here we have on the left, we've got a blast with the waste hidden. It's a copper blast, and this is post-blast. So you can see that the change in shape of the ore body of the model. And if we look at this, sort of vein which is sticking out here, you can sort of see it's moved, from here to there, like so. So it's moved, it's been translated. So if we take the 2D translated polygon and process it, in this case, we actually did a campaign with it. The mine more or less thought it was, with that 2D translation, that the contents of that polygon were the same pre and post blast. But we know that it's not. So we campaigned that polygon in the mine, and then we looked at what we got in terms of the copper at the concentrator, and also some other variables. You can see here that the density has changed quite significantly from 2.8 tons per meter cube to 1.6 tons per meter cube. And that's because everything swells. Once you blast it, you get the swell factor. So the bulk density drops. When we campaigned it, the feed grade to the mill was recorded at 0.5%. So which aligns more or less to what we had predicted. And why do they change? Well, because some rock moves up, some rock moves down. This is a slice through that blast. The mid bench boundary, you can see how that changes. So everything moves horizontally towards the free face, but there's obviously a lot of movement, so that needs to be taken into account. Kinross, who were our initial sponsors of the software, did a 3-month trial where they've paid for OrePro's development. So they took 3 months of our polygons and campaigned them through the mill, and then also did a back calculation to see what would have happened if they used their old 2D methodology. And they were experiencing a lot of variation, up to 17% variation in that differences in the reconciliation. After the 3-month trial, we got numbers which were like within 1%. So we're obviously doing something right here. If they'd processed the ore using the previous 2D blast mitigation process, they would have been out by 15%. So quite a significant difference here, 11% difference in ounces. So convert that into dollars, and you can see why this is a big deal. So the story is we need to accept that the ore body changes shape, and not to try to connect the pre-blast to the post-blast. The post-blast is new. So, and sometimes blasting affects the value, but other times it increases it. Blasting always affects the value, but sometimes it reduces the value of the recoverable metal and sometimes increases it. So in this case, it's increased it by about 10%. And what that's done in this case is that the material is now being smeared a bit so that you're able to target something which might have been small pre-blast is now being spread out post-blast and is now recoverable. That's not always the case, but you do have to blast it, unfortunately. That's just how it is. So that if we look at this is the data from the blast in the beginning of my talk. So we look at that in terms of results. So it was a 10-meter bench, and that was mined in 4 passes. So the mine measured blast movement, and they moved the polygons horizontally, and we did a comparison between what what our polygons would have recovered and what the 2D moved polygons would have recovered. And in total was, for this single blast, was $720,000 in value. And that is in a reduction of nearly 5,000 tons of dilution. And that's material that you send to the concentrator and doesn't give you anything. And probably more significantly, the ore loss of nearly 10,000 tons, which goes to the muck piles, to the stockpiles and waste dumps, and you never see it again. Perhaps in a couple of 100 years that people may go back and make some money out of them. Another case study, structurally controlled gold mine, which you'd think is fairly straightforward, 10-meter bench. Here we're looking at different dig directions. So we've got digging to the south and digging to the west. So the difference between what we had generated and what the 2D movement was between $120,000 and $260,000, depending on the direction that you dug. And between our polygons is $225,000 in mining direction. So very significant numbers. And these are for single blasts. So you multiply that by a couple of blasts per week, and the dollars do add up. So I did mention that we have these smart vectors. How accurate are they compared to actual physical measurements? We have got access to thousands of blasts now, and we've learnt a lot in the last 10 or so years, and we're getting pretty good accuracy. So in this case here, we're comparing our smart vector versus a measured vector in the exact same location. You can see we predicted 6.76 and the measurement was 6.54. So obviously, this is, sometimes if you're in high powder factor blasts in chaotic regions, sometimes you do need to take these measurements. And, but we've seen that the smart vectors are holding up pretty well. Where are we going? I'm going really fast. Where are we going? We're looking at, where are we now? So we've got 30 clients around the globe, and that's been in the last 18 months or so. And we've recently partnered with Sequent, who are a New Zealand software company who do Leapfrog. And it's actually very good timing because we kind of joined up with them pre-pandemic, and they have 15 offices around the globe. So that kind of gives us footholds in regions that we couldn't reach otherwise. So that's been quite successful. We're looking at augmented reality. That's on my kitchen table, obviously. We would like to take that out into the real world. We're working on a product called BBP, which is Bench Blast Planner, which will allow you to look forward and get a bench worth of data and predict or evaluate what's the best direction to attack the next bench. So that will take a bit of modeling skills, but we are working on that. It's really just to give you an idea. Should we attack this bench from the north or from the west? And also recon. So we would like to implement some reconciliation capabilities to actually track how we're performing. And of course, continued collaboration with our friends in industry. So that has driven a lot of our innovation is getting feedback from our clients. And we know most of our clients personally. And yeah, we just want to develop something which is top class grade control product that we'd be proud to call our own. So what about coronavirus? What's the like tenuous link between grade control and coronavirus? Many of our clients are actually experiencing limited staffing due to social distancing constraints. So it's either people aren't able to get to sites or they're socially distancing on the muck piles. So OrePro has allowed them to do to turn around their grade control processes much quicker, and without I guess infringing on these social distancing limitations. So between going out to between getting the Postblast scan, which is about an hour with a with the drone and the software, and delivering those polygons, we can probably do that in 10 minutes. So it's quite a quick turnaround. In addition, the lockdowns have imposed a new reality on us. Will, in particular, had spent a lot of time on planes, flying to the middle of Africa for a 3-day course and then coming back. So what it's made us do is, have a good hard look at ourselves and look at how we can tackle training and things like that. So we've concentrated on a lot of remote training packages. So not just in static material like PowerPoints, we've also developed a learning platform which allows us to allows our clients, with really poor internet connections, which a lot of our clients do, to download our training material and store it temporarily in our platform, protecting our IP as well. This is our livelihood, so we want to protect it. So yeah, this has given us an opportunity to develop these tools. I thought I was going to go over time, but I haven't. So my takeaways, as Nathan said at the beginning, there's always potential to innovate and improve something. If we thought that the sensors that we developed 20 years ago, 17 years ago, were it, we solved grade control, then we would have sat down and gone and done something else. But there's always room to improve something. Look at Apple. Don't look at Nokia, but look at Apple. Find clever people to work with. Don't think you're the cleverest person in the room. There's lots of clever people around, and everyone's got a different point of view and different angle on things. And finally, just be nice. Don't be evil, as Google said. The mining industry is a nice big sand pit to play in, and I think everyone can play happily there. And that's it. I'll have to remember next time that. Thank you. I'll have to remember next time more than, slow down or whatever.
Oh, thanks very much, David. That was a really stimulating talk. Really interesting to see your developments there. We haven't got any questions yet online. I don't know, Rick, if you have any from the audience there. I'm sure there's going to be plenty of discussion.
Questions from the audience?
Yeah, I'll start.
Of course you will.
Well, I've always found fascinating the fact that you've been digging it, and I think that's the highest trend you have, is that you're getting the dig direction and the digging process in there. And anyone who's worked with disparate data, as I have, has always had this issue with reconciliation. Now that you've done that, you've shown that you can sort of match plant with what you predict.
Mm-hmm.
How would you plan a mine differently, considering that your mine plan and the way you've operated your mine up to this point with the bench affects your impact of choosing a digging direction? So I'm just asking you, it is a very general question, but I think it's fascinating that now that we can link everything, maybe we need to go back and rethink the plan.
Yes.
So what have you learned?
So the bench blast planner, which we're working on.
Can I just interrupt?
Sure.
Nathan, could you hear that question?
No, we didn't hear the question. We've had a comment from somebody online saying.
Yeah, okay. I'll repeat the question. So the question is how does our how will our methodology affect mine planning how will it possibly affect mine planning? So this bench blast planner that we're working on is meant to do just that, allow you to look at a bench and look at the differences between attacking from one direction versus another. So there are a few things we have to do to get to that point. So one is that muck pile prediction, because that's critical input to our algorithms. But I think if we can get it, if we can use something which like VBOC with that sort of something with that resolution, if you like, that should solve our problem. So we have the framework in place. So if we've got, what's a bench? 100 blasts, I don't know, 50, 100 blasts, depending on the size. We could easily run run a whole number of scenarios on a bench, overnight, whatever, and say, okay, attack it from the west. Obviously, you can't attack a bench from the same direction. So we could then add some flexibility there to change directions as you go. So yes, I think that there's big value there, and a number of our clients have asked that. Actually, last night, we have a help platform, and one of our clients asked that. Says, can we use this to predict for the next bench that we're going down? So yes, that's where we're going. And it's not as simple as, maybe some deposits have got a nice cleanly defined vein, which is in a particular strike, but a lot of operations aren't. A lot of operations are twisted, and there's money to be made by being very specific in the angles of attack that you excavate, and also the flitch heights as well. Whether one bench is one blast you can do in a single flitch, and another one you can do in 4 flitches. So we can do all that. We just have to get the platform in place.
Okay. And David, I've got a quick question. I think it's really good to see your partnership with Sequent. Are you already seeing integration of geological models into your blast design, or is that something that may come down the track as you start evaluating controls and factors?
Yeah, still early days. The idea will be eventually, we don't want to be limited to a particular package, obviously. We've been fairly open with how we import stuff. So at the moment, we're just using CSVs. With a few bespoke packages that we're allowed to import. But yes, we think that that space is ripe for development or innovation, if you like. So yeah, that is somewhere where we're moving, hopefully with Sequent in particular.
Oh, that's good. We've got a couple of questions online. I'm just going to try and combine a few because there's a few people that are interested in a few things, mainly around the sensor technology that you might combine with this. Is the approach to blast tracking, how does it compare to in-shovel grade measurements? I suppose probably more from your base metal operations as opposed to gold. So how does this work in terms of a kind of a more reactive approach versus a kind of a planning or scheduling approach?
So you mean if there's a sensor on the shovel bucket?
Yes, I think there's a question from Nick Redwood that was asking basically how does this approach to blast tracking compare with in-shovel grade measurements? So the kind of the reactive approach as opposed to this kind of predictive. Yeah.
Okay. Well, we haven't looked at that level of that resolution of reconciliation. So most of our clients, well, as far as I know, none of our clients use sensing technologies in that way, but there's no reason why we can't. That would be an interesting exercise to compare what we predict to what's being measured. We have done a little bit of work with BHP doing digital digging, so digitally excavating the post-blast muck pile, and that has some assumptions with regards to a bucket is X tons, and you then you're sort of going into the space where you have to take rilling into account and things like that. So it is possible that going down to that granularity of the shovel may be a bit noisy, But certainly we'd be, if one of our clients is, if anyone wanted to test that out, we'd be open to that.
So I suppose follow-up questions. There's a question from Lee Poulin and Henry Kerr. Again, just wondering, probably more towards your day job there, is questioning how these will integrate with in-pit ore sorting, screening, and sensing equipment in the future, I suppose, if you haven't implemented those at the moment.
No, we haven't as yet. Again, the data will be there. It just means we have to. At the moment, we're looking at reconciliation of polygon by polygon. So we haven't drilled down to be looking at material excavation on a hour by hour basis. As the dispatch systems become more and more accurate, I think that will open up the door to us investigating that. But no, we haven't implemented that today. There's no reason why we can't, because we have the Postblast model. So it'd be an interesting exercise.
Okay. Rick, have you got any other questions from around the room?
I don't know if you can hear me. I hope you can. Well, we've got one from Italo here. I can see. Is this development making blast movement sensors redundant?
Not just yet, Italo. You still do need to use blast movement sensors in some scenarios. As I mentioned, if you're in high powder factor situations in chaotic regions, yes, blast movement sensors have their place, but we're not at the redundancy level just yet. And that is, I might just want to emphasize, it's not what we're trying to do. We're doing our thing, but some of our clients don't have sensors. They've got pieces of bamboo or polypipe. So we have to make do with what we're given. So that's why we developed this. And also, as I mentioned, if the clients allow us, all of their blasts get pushed into our cloud. So our algorithms are learning. So we've got a bit of machine learning going on there, learning from all the previous blasts. At the moment, it's thousands of blasts. So I guess we're building this big machine learning algorithm, which is continuously learning and becoming more and more accurate.
Another question.
Sorry, last question. I've run into a lot of customers that don't believe that the post-blast surface is an expression of the internal movement. And what you're basically saying with your smart vectors, that they most of the time will work, it means because you're calibrating them to the final surface, you're basically indirectly saying, well, the post-blast surface is an expression. The blast will,
yes.
Improving it.
It has to be. Yes.
Can
yes.
you publish it?
We will.
So that I can use it?
So, yeah, sure. So the question was, well, the statement was that some of Connie's clients have said that the post-blast surface does not necessarily represent the movement below. I find that, it's kind of a no-brainer, I think. Let's take a simple example. Let's look at the front of the blast, where if it's a free face and you get your typical muck pole shape and you get everything kicked out, it has to be a reflection of the movement. If you've got 30 meters of movement, which some of our Mexican friends do, the front of the blast moves 30 meters and you've got this slope which goes out 30 meters. So it has to be. Maybe sometimes it's not, but the way we visualize the rock mass is as a fluid. In that quarter a second, half a second, I know it's a bit hard to comprehend, everything gets fluidized and gets kicked forward on the gigajoules of energy that are within it. So whilst sometimes it's uncontrolled, it does flow in a particular way. And we've seen that time and time again from measured vectors and from our smart vectors after that. So I guess prove it, I suppose. Yeah.
One more question from an online attendee, Mark Knopp. He was just wondering if you could apply some of these modelling to movement in a cave, either block cave or sub-level caving?
Yeah, we've had some questions. We've had a lot of webinars this week, and there's been a lot of questions about underground. No, we'd love to. No, I would love to, because that's just my nature. But no, we're not looking at underground just yet. We'd have to look at. I know there are cave markers out, cave trackers out there. So we'd have to look at some of that data, but we're not going to go there. Possibly, but we're not looking at it. There was a question there about fragmentation.
Yes.
Yeah, we've had that a lot as well. Again, the possibility. I would like to incorporate fragmentation. Oh, sorry, you can't see. Yeah, sorry. Yes, sorry. There's a question about incorporating fragmentation into the model. We don't have fragmentation. We could do fragmentation, and because there's nothing really out there. I think all the consultants hold their fragmentation models close to their heart, because it's part of the value prop. We haven't done it yet, Mohsen, but I would like to. But I just have to convince my partner to allow me to do that.
I had a question. It's probably lots of people who know the answer to this, but it's not my specialty area. You showed that really complicated decision tree, for controlling what the trucks do when they're actually, mining the material that's been blasted.
Yeah.
How do you actually implement that with the trucks? I mean, is your software interfacing with software or heads-up display or something that the drivers are seeing?
Did you get that, Nathan?
No, I didn't. Sorry.
Okay, so the question was that complicated decision tree. How does it manifest itself with the trucks? So what happens is that we create the polygons, and the polygons get given a label, which is a destination, and that gets pushed out to the fleet, the FMSs, the fleet management systems, modular or Wemco, and that system. Yeah, so there are heads-up displays which have that polygon. So this polygon will say this is high grade, which may go straight to the concentrator or to a stockpile. So that gets put into the heads-up display and the shovel, and the operator will dig, knowing the dig direction, and will dig until those lines are met, and will load that truck, and that will be the destination for that truck. If another one is acid generating, it'll go off to the acid generation stockpile. So that's how that works. Yeah.
Okay, I think there's just one last question. You can probably see it on the screen there from Ian Lipton, but I'll read it out loud anyway. Do you use simulations or multiple realizations as part of the optimization of the dig line? No, we just take what's in. I'm not really in that space, but we just take what's in the grade control model. So if what's in the grade control model is multiple realizations, then we can do it. But no, we don't do any multiple realizations at this point in time. We've only been going for about 18 months, so we need a bit more time. Excellent.
Have you ever done, and I probably know the answer to this, but I was just thinking, it sort of follows on from Connie's question. I could imagine a situation where, if you were taking it back to planning everything down to the digging directions at the sort of pit optimization stage, have you ever done any sort of back of the envelope calculations of the overall extra value you could create by doing that?
Yeah, the question was, have we done any back of the envelope calculations on what's the value that could be realized if you optimize at a bench by bench sort of scale? Correct? Yeah, it's millions and tens of millions of dollars, really. Yeah, you can see that those numbers are not, we didn't pluck these numbers that were like, oh, this is amazing. It's consistently, hundreds of thousands. Well, I'm not sure what the average is, but it's consistently a significant multiplier of the cost of the software per blast is on average is the value you get back. So multiply that by the blast on a bench, and that's your number. Yeah.
Any other questions here? Back to you, Nathan.
Okay, that's great. If there's no other questions, I think if we could have another round of applause for David from the audience, that'd be appreciated. Thank you.
Thanks, everyone. Thank you.
And yeah, I'd like to say thanks again, David. It was really a really excellent talk. Really good to hear your current work. It's really good. We haven't got a speaker lined up for next week. We had an unexpected cancellation, but we'll be working to find a new speaker for next week, and we'll let everybody know by LinkedIn who the speaker will be. But for now, I'd just like to thank everyone again, and I'll stop broadcasting from here. And David, feel free to obviously mingle and socialise with it.
Socially. Yes. Okay. Cheers. Thanks, Jason.
Thanks again.
Bye.